Welcome back. I guess you're getting pretty excited about this modelling from data. You can see the usefulness of it, I guess. You do an experiment or somebody collects data and you as a budding young mathematician can analyse it and find a formula to describe the trends. That's what we're aiming for. So just remembering back to what we were doing here. And we were saying, well, we could get to a point of graphing the data, and that was the, this one here was the calculator graph, and this was the hand-drawn one of the spring and the length and the mass, and looking at the relationship between them. But we found an R-squared, and we're trying to understand that that measures the amount of association or correlation between the variables, and it was positive and pretty high here. This is a pretty good line here, picking up most of the points. But where should the line go? How do we tell? And down here, we've got a spreadsheet to help us. So we've got two forms of technology we're going to look at in this presentation. The graphics display calculator and something like a spreadsheet like Excel, for example. Let's go down and see how we do that. Well, here you are. We can say, well, this is a pretty good looking line here, and we call this the line of best fit, the one that we think fits the data best. And the question is, what does best mean mathematically? And this one might have been drawn by eye, just putting a ruler through and trying to find the position where the points get closest. All the points are on or closest to the line. That's just a reasonable basic starting point. But what does best mean mathematically? Surely it doesn't mean just line it up, because we've learned that in maths, graphs are fairly inaccurate, aren't they? If you just do it by plotting by hand and so on. So we really do need a mathematical technique. So come on down and let's have a look and see if we can discover one here. And here's our first idea. We're going to draw a line through there, and we're going to call this our model for the data, isn't it? Remember, the model is mathematical description of a practical situation. And the model here will be something like y equals, and we call it y hat, because it's not the actual y values, no, not these actual y values, but the model where we are trying to create a formula which best describes the data, if you like. So it's y hat. And we want to measure how close the data points were away from our proposed model. Get the idea? So this is a possible line of best fit. And we're going to start our mathematical journey by saying, let's try to measure the residual deviations away from the model. We put the model in and then we look at it and say, hey, hang on, there's still some error here, or regression. And there's another word, we're going to bring that in. The lines are regressing or coming back off the point, off the model. So by how much? What's the residual deviation? What's left residing there? Get the idea? So there's a few little mathematical terms. And as usual with maths, the language is pretty consistent with English. So if you say residual, something's residing, something's left after you put your model through, and that's deviations away from it by our original data set. Okay, let's build on those sort of words as we come down here now. And wow, look at that. It's called the least squares line, or a regression line, and this is what the calculator and spreadsheet will do for you mathematically. Okay, rather than by eye. The least squares line. We're going to talk about the least squares there in a minute. And you can say, well, here we are. What's that? That's the slope of the line of best fit. Well, you might say, thank you lucky stars that we don't do the maths of that in this course, and the C value is this complicated looking formula. So you don't actually have to use this formula. We're going to use technology in this course to have a look. So it's called the least squares line. Now, why is it the least squares? I wonder if you can think about that. Okay, well, let's come down here. We might have a look at technology in a minute. But can you see that if you had a point above and a point below, if you just looked at the deviations of those away from the model, so y take y hat, some would be positive, be above the line, some would be negative. And they would tend to cancel each other out, wouldn't they? So if you summed up all the regressions, that is, the deviations away from the model, then you may well get zero, thinking you had a great model. But they could be quite a long way out. Okay, so what we do is we square these deviations. We're going to look at, now we don't have to do this, but in finding the least squares model, or the linear over here, come over here, linear regression, how much the points regress from the model, we use squares. So the deviations up here don't cancel each other out. We're trying to find an overall sum of all the deviations, so we use the squares. Because if you square them, they both turn out positive, don't they? And you'll add up the effect. Now, because it's a square, we want to minimise that now. Well, not because it's a square, but we will minimise those squares of the deviations. So we get the idea of least squares regression. Least squares. We've got to find the least value of the squares of the deviations. Okay, get the journey. I hope so. Anyway, let's have a look. We've already done this in the previous presentation. Just remember, we got to this window by going to Stat Mode, entering the data in List 1 and List 2, setting up the graph, selecting which one we would draw, and then choosing Calc at the bottom of the graph, and then choosing X for linear. And we got this window. If we then push to execute, it will fit the line that it's talking about here, and that was the point we got to. So we already have looked at, and we chose this one generally because it's like y equals mx plus c, which a lot of people use. So we've already had a look with the graphics display calculator at how to generate that line. Please remember these steps and be able to generate that line and its formula. Don't forget to put in a contextual formula here. So length of spring and mass you'll use, not y and x. You can write it down for the calculator with y and x, but then you've got to shift it into the context of the question. Okay, got the idea? All right, now you've done that, so revise that. Let's look at the spreadsheet now. Let's look at using Excel. So with Excel, you open it up and you put your values in, the x and y, if you like, if you want to work in x and y land. But you could use x as mass and y is the length, so that would be fair enough. But then you highlight this set of data, or just highlight the scores, sorry there. Okay, highlight it and choose the graph wizard, or here it's showing a scatter graph. And you'll get this, and you can edit this. You can edit the scale. They haven't labelled the scale here. You can label it M and L. It should be labelled if you highlight the whole thing and you're using M and L. It will draw the line of best fit. And if you right click anywhere on the graph there, right click, it will give you the option of showing R squared and a trend line. So it will display everything on that graph for you. Okay, so play with that, because in everyday life, people don't tend to use calculators, use spreadsheets in business. So there's our trend line. So have a bit of fun with that set of data with the spring using a spreadsheet. All right, we'll come down and let's have a look now at the idea of using a calculator now, because it's easier than the spreadsheet, to look at the residuals. What we're going to do is try to analyse, right, the residual deviation after you fit the line, how much deviation away from the model still resides. Analyse residual deviation of each point. Okay, you'll see this come up now. So how do you get the calculator to measure the residual deviation? Come to this window here. So you've got to go Shift to get to this window, Shift and Menu. And then it's a Stat window. And here's what we want, what's highlighted here. You might not have even known it lived in the calculator, residual list. And usually it's none. But you will hit List here and put it in a list which is convenient to you. So if you put your data in List 1, List 2, you might do what I've done, put the residuals in List 3. What it's telling the calculator is calculate the distance of the original data point, y's, away from the new model that's been fitted, and stick those deviations in List 3. Now you've got to do this before you calc. Right, so you get to this point, set up your residual list before you hit F1 in here to calc. Because when the calculator does that, it will do your residuals and over here and stick them in list 3. There's no good pushing the residual list after the calculation's been done. The calculator's lost that data. So now you hit calc and choose this, and we have a plot. And at this stage, the calculator will enter the residuals in list 3. Come down and have a look. Look at them, they popped up there. So you've got to go exit, back to the first stat window, and there's the residuals. Okay, so now you want to have a look at them graphically. So go to graph 2 and set it up. So it'll be a scatter graph. This one has got to still be the same list values. Now you're plotting as X goes up or as M goes up, the list 3 values, which are the residuals, and here they are. Now they've exploded a bit. They usually, with the calculator, really blow this up, so it makes it look as if the points are a lot further away. See, this is the 0 position. That's where Y exactly equals the model. And none of them are perfect. Some are above that one and some are below. But they are a lot closer. Let's look at the real graph here. The residual list has blown them up. See, this one's quite close, but it appears down there. This one seems quite close, but it's above. This one seems quite close to below. So you've got to be careful with the scale of the residuals there, because the calculator tends to blow it up to get a good look at it. So this one appears astronomically high up here. This one is down there and so on. So can you see what we're doing? We're plotting the Y take Y hat. How far away our data set is from the appropriate model value, Y hat. Okay, so that gives you an idea of how good the fit is. This is a bit misleading, this graph here, because of the expanded scale. But it does give you an idea of the distribution of points. So they're quite good. They trap the line. I like to call this trapping the line between the points. So you can't deviate out too far outside the points, can you, to be a line of best fit. It traps the line quite well, the points. And just remember here, this scale is when Y equals Y dash. So there's 0 deviation, and that's what you want. You don't want too many points too far away from the model. Okay, you get the idea. It's starting to build up. This is really a concept for a Year 12 course, so hopefully you can get hold of that so you understand it better later on. Let's go down now and have a look at this question. A red hot burning question here for you. What properties should the model have? How do you determine whether it's a good fit or not? Okay, let's go down and see if we can think of some things. And as we do this, what can we think about that would determine whether we've done well with the position of our line? Okay, come down here and let's have a look. Here we are. All points should be on or near the line. That seems reasonable. Points should be randomly distributed, not a whole lot off at one end. So here it might be going like this, and then we've got something like that. Hey, you can't do that. Well, you could if they were outliers, couldn't we? So we've got to consider outliers. But what we're looking at here is plotting the data set after the outliers have been removed. Okay, and seeing if we can fit a model. We'll see a couple of problems from Hayes and Harris in a minute. We've got some screen clippings there from Hayes and Harris, so you should get hold of their book. But we'll see some good examples of removing outliers. R squared should be checked. Now notice R squared should be checked as the last point here, because quite often you can get a low R squared through the balancing out of points, but the model is not necessarily good. Okay, so you come across that again later on in Year 12 course. So let's look at the one we had. Let's inspect the graph. Yes, it looks as if each point is on or near the line. Then it also looks like they're randomly distributed. But if we wanted to look at random distribution, we'd look at the residuals. So this is the 0 position. This is where Y take Y bar is 0. or the points are exactly on the model, right? So it's expanded a bit, but you can see, yes, it's basically a random distribution. One above, one below, one above, one below, one above, one below, or this one is also below. That ideally would be up there. You see the idea of trapping the points, trapping the line between the points. Okay, the line must go between the points to be a best fit, if you like, either by eye or by the least squares regression method. All right, so they are the points, aspects that we want here to check out, to check whether the line is a good fit, the model is fitting the data well. All right, come down and let's have a look now using the model. Okay, what are we going to do? There are two things we can do. First of all, let's look at this diagram from Mays and Harris. Here we have the independent variable. Here it was mass, we're just calling it x here, and this was length of the spring. Okay, so here's our data set. We measured from here, and they're calling this the lower pole and the upper pole of our data set. Now, the first thing we can do is what I put over here to estimate points which are missing within the measured data set. So, in other words, when the mass was that, what would you expect the extension to be? Using our line of best fit. So what we're going to try and do is that. And that's interpolation. Inter means between. Working out values between the given points or the data set. Points are missing within the measured data set. Now, could that be good? Could we find a reasonable, would that be reasonable to do? Okay, now, there are a couple of conditions here. It would be reasonable, we'd expect, if the line was a good fit from our observations, and that would include looking at r squared high. So if the line was a good fit by all points being on or near the line and random distribution and r squared high, we'd probably say give that a couple of ticks. Yep, should be okay, shouldn't it? This one's not bad here, but it's not terrific, but it's reasonable. All right, what about going outside? Here they've used a word called extrapolation, extending outside the particular range of the data set. Come down, I've got something to say down here for you on that. Now this is dangerous, so it's in red. Please note that. Extrapolation is dangerous. We'll talk about that in a minute. But what you're talking about is saying, using the model, which is our y hat here, to predict outside there and down here. Extra points outside the range. And this is generally unreliable. Generally unreliable. So this is something you should say. Even, this is hurting, even if the line is good, line is a good fit, being done by least squares regression, and it looks good, random distribution of points, and r squared is high. Even if that's the case, we can't say extrapolation is going to be reliable. Why? Why do you think? Think about the spring. Why do you think extrapolation might be unreliable? And this is the standard response, so please learn that. And then you've got a comment as well. Because even if the line's a good fit and r squared is high, extrapolation, getting extra points, is likely to be unreliable. Likely to be unreliable. Here it is. Danger. If you go outside of the data set, it assumes the conditions which gave rise to the data have remained the same, allowing the trend to continue. Let's think about our spring. Let's think about putting bigger and bigger weights on it. I guess you've done something like this with wire or springs or something. Can you see that for high masses, mass going up, the elasticity of the spring might be exceeded, and it would now sag, and it wouldn't keep on that nice growth line of y hat. Oops, not y hat now, is it? L hat, isn't it? The length. It might not keep going because its elasticity stops, is exceeded. And what about going down? If we had small weights, they might not be heavy enough to extend the length of the spring in the same way. So can you get the idea in practice in the context? And this course is a precursor to a course which is very focused on context, making the maths work in a context, very much centred on modelling, looking at a practical application, coming out of X and Y land into the practical world. All right, so that's very important. Remember, extrapolation, generally unreliable, interpolation, generally reliable, given best fits and so on. Okay, and you might use this sort of comment. The trend could continue if the conditions giving rise to it were maintained. All right, come down and let's look at a good example here from Hayes and Harris. So table below shows the sales for a book business. Draw a graph to illustrate the data. Find R squared using technology. Find the equation of the line of best set using a linear regression formula. We're not going to do that. We're going to use technology in this course. Predict the sales figure for year 2003. That's out this way. Give your answer to the nearest $10,000. Comment on the reasonableness of this prediction. Okay. Let T be the time from 1995 and S be the sales. Notice you generally don't put 1995, 1996, the numbers are too big. So usually measure it from a fixed starting point and time means in simple years from starting from that time. And we get a nice graph. And R squared is high, line of best fit from the calculator is that. Okay, don't forget here, contextual, don't put Y and X off your calculator. That's technology helping you. You must come into context, so please note that. And again up here with the graph, please make sure you've got good scales and the axes are labelled. I'm going to keep pounding this word, context. Okay, now let's put in 2003, so that's 8 years from when we started. And our prediction would be, notice the use of the approximate sign or this squiggly do, I like that one for approximately. And we come up with 2003 would have sales of approximately 350,000 because these are in 10,000s here. And that should be mentioned up here as well, 5,000, 9,000, etc. So that should be, the units should be written like this, thousands. Okay, thousands of dollars actually. All right, so the predicted sales would be 350,000. What do you think? You're coming off the end here, and it's extrapolation. Okay, so the R squared value suggests a linear relationship is very strong and positive. However, since this prediction is an extrapolation, it will only be reasonable if the trend evident from 1996 to 2001 continues to the year 2003, and this may or may not occur. That's a very, very good statement. Okay, so you should say, hey, I'm pretty happy with this line. I'm going to give it lots of ticks down here, but we don't know whether that trend will continue. You might get a competitor who starts a big advertising campaign in sales. So you don't know. Or you might start a big advertising campaign and up they go that way. Get the idea. This is interesting stuff. Modelling from data and using it in the real world. All right, it's your turn. So come down and I want you to go through the sets of data you did before. This time, checking your technology with a spreadsheet and also to do some interpretations here. What does the slope mean? As the mass of the spring increased, what was the change in the length? All right, remember what the slope means. And the vertical intercept, when m is 0, what's the length? What does that mean? Okay, and then do some predictions and comment on these predictions. Okay, pause the presentation, have a go. You've done part of this back in the last presentation in 2G1 from Hayes and Harris. So now check it and go on using your model. Let's have a look at question 2. There's question 2, a bit of question 3 there. Think about the context of the question. Discuss it with your teacher and classmates. It's interesting stuff. And question 3 is very interesting. Okay, so have a look at question 3 in particular. Big discussion needed there. All right, I'll show you the answers now. There's question 1. Coming down now, let's look at question 2. And very interesting in question 3. Okay. Well, I hope you're getting excited. It's starting to push along now. And what do you think is next? Well, we talked about linear modelling, but maybe some things follow growth curves, as we've seen earlier in models of growth. So we're going to have to look at modelling those too, aren't we? I hope to see you in the further presentations. Cheers for now.